In space, no one can hear you scream. But at least someone might see you. But what if they never see you? What if there's a point so far away where Earth moves faster away from you than any of your signals? Well, then maybe by waiting, Earth would slow down and you could send your SOS. But what if there were a point so far away that your signal could never ever reach Earth? Then you would be stranded forever. The scary truth? There is such a point. This point, along with the point where you would have to wait, are 2 of 3 points that we call the cosmological horizons of the universe. The speed of light is the fastest speed at which you can travel within the universe, and it isn't infinitely fast. This is, for instance, why it takes 8 minutes for the light of the sun to reach us, meaning that when we look at the sun, we're actually looking 8 minutes back in time. As you look further away, you look further back in time. So what we see of the Andromeda Galaxy is about 2.5 million years old. If you look far enough out, you will see things from the very beginning of our universe, like the cosmic microwave background. The more time that passes, the more we are able to see. But there is a limit to it all. This limit is the first cosmological horizon, and it is called the particle horizon, the edge of the observable universe. The cosmological horizon expands as the universe ages, allowing us to see more and more of it. But this does not mean that all of the places we see are reachable anymore. If we one day saw an alien inviting us to tea, we might never be able to go meet them. Even if we found a way to travel at the speed of light. This is due to the expansion of the universe. When the universe expands, everything moves further away from each other. For us down on Earth, this is barely noticeable. You don't see your neighbor's house sliding away from yours. But when you look further out, this expansion starts to have a noticeable effect. For a galaxy far, far away, this means that it would be pulled away from us faster than the speed of light. If that is the case, we wouldn't be able to reach it right now. But this doesn't stop us from greeting our alien friends, does it? Well, not yet. The trouble comes from the way the universe expands. You see, it doesn't expand at the same rate all the time. The rate at which it expands depends on something we call the Hubble constant. And simply put, if the Hubble constant is above 0, the universe expands. If it's below 0, the universe compresses, and at 0 it stays constant in size. Right now, the majority consensus among astrophysicists is that the universe is expanding, meaning the Hubble constant is above 0. However, this expansion is slowing down as the Hubble constant is nearing 0. This won't last forever though, and most astrophysicists believe the expansion will accelerate again, and will then become faster and faster until the end of the universe. Because of this, if we send a signal back to the aliens, it might be millions of years between the time the aliens send out their signal and the time they received ours. And in that time, the universe could have begun accelerating its expansion, which could mean that the galaxy in which the aliens live is now traveling away from us with a speed higher than that of light. Our response would never arrive. The point at which things move away from us at the speed of light forms a barrier around us. This barrier is called the Hubble horizon. The Hubble horizon is not constant. It changes based on the expansion of the universe. The faster the universe expands, the less distance there is to the Hubble horizon. In fact, if the universe were to shrink, there wouldn't even be a Hubble horizon, as we would be able to contact the entire universe. In the current day, the Hubble horizon is expanding as the expansion of the universe is slowing down. Because of this, we get to interact with more and more of the universe each day. This will not last though. Unless the expansion of the universe stops, there are some places in the universe with which we will never be able to interact. Some aliens we will never quite reach. And this limit is called the event horizon. not to be confused with the event horizon of a black hole. The two share the same name because they work the same way. Essentially, they're the point at where no light, or anything else for that matter, can ever reach us. Now, where the Hubble horizon is the limit for what we are able to interact with at the current expansion of the universe, the event horizon is the limit of what we will ever be able to interact with. It lies between the particle horizon and the Hubble horizon. So we can see planets, stars, and galaxies beyond the event horizon, but we will never be able to impact them. And we will never know what happened to anything from the moment the event horizon swallowed it. The gap between the event horizon and the Hubble horizon is always shrinking, and the two will eventually collide and become one. In accordance with this, the Hubble horizon can never move beyond the event horizon. Here, it is important to notice that both the event horizon and the Hubble horizon both only exist when the universe is under certain conditions. You see, the Hubble horizon is defined as the radius at which the universe is moving away from us faster than the speed of light. So if the universe is contracting, there is no Hubble horizon at that moment. The event horizon, on the other hand, is defined as the radius at which no event from now on can ever affect us. But if the universe ends in a big crunch, we know that everything will become infinitely close. And so all events will end up visible at one infinitesimally small point, where we too will find ourselves. So if the universe ends in a big crunch, there is no such thing as an event horizon. Notice here that there is a difference between the two conditions. The Hubble horizon can be non-existent 1 minute, then exist another, then disappear again. The Hubble horizon is a momentary description of how the universe behaves. But the event horizon is set in stone. If it exists at one point in time, it will exist forever, because if it could disappear, it would mean that any event from that moment on could affect every other event, and these events would have been affected by all former events. So by definition, the event horizon can never disappear if it already exists. Notice then that any object from outside the event horizon can never move inside the event horizon. And because of this, the event horizon cannot expand faster than the expansion of the universe. At the event horizon, minus the speed of light, as this is the fastest anything can move at the event horizon. And because the event horizon is usually pretty close to the Hubble horizon, this means that for all intents and purposes, the event horizon is always shrinking. Now that we've covered the different cosmological horizons, you most likely have an idea of how the different horizons work. But the beautiful thing is that this is physics. And physics is just a perpetual endeavor to create more and more accurate models of reality. So, as physics students, we should be able to model these horizons mathematically. Now, first, as a physicist, it is always important that you lay out all of your assumptions before moving on to your math. This way, if you end up with the wrong model, it's not your fault, it's just that the assumptions were wrong. So we will assume a flat universe, meaning we can use the Friedmann equation to describe it without taking curvature into consideration. A is called the scale factor, and it basically describes how a distance between 2 points in space changes over time. Notice the omegas in this equation. These are constants for the distributions of matter, radiation, and the cosmological constant, which cosmologists usually describe as some form of dark energy. Different values of these omegas correspond to different models of our universe. The values we're going to use in this example are from an assumption called the benchmark model. For all of the cosmological horizons, we need either A or H, so we better solve this differential equation. You can do this any way you like, but we did it numerically using Python. We got a scale factor that looks like this. The axes are pretty confusing, but the point is that the scale factor basically does not change over time. This is actually still okay, as small distances don't change much. The big issue is that this model doesn't seem to include inflation, which was a period where the universe expanded very, very rapidly. An easy solution to this issue is to say that our example only simulates the universe from the point in time where inflation ends. Then our model should probably hold. Now let's take a look at the horizons. The radius of the particle horizon can be described by the following integral, or you can do a substitution and get this integral instead. When we did this, we got the following evolution of the particle horizon. If you look at the end of the graph, you will see the particle horizon at our time measured in light years. The value in our model is 14 billion light years, whereas the real radius of the particle horizon is about 50 billion light years. That's a factor of 4 in difference, which is a pretty good result in astrophysics. And since we know that the particle horizon is very dependent on the evolution of the universe, it is easy to see that our error probably comes from not including inflation. To find out the radius of the Hubble horizon, you have to divide the speed of light by h. When we did this, we got the following graph. After an entire night of computation, our editor realized that he had used seconds instead of years. So technically the Hubble radius is here measured in light seconds and not, as it says, light years. When we account for this, we actually get really close to the real value of the Hubble horizon. The event horizon has a radius given by the following integral. When we ran it through our script, we got this evolution. Here we see a big problem. We claimed before that the event horizon would always be shrinking, but this model of our event horizon is growing faster than the particle horizon. This means that there are some big problems with our model. This happened because our program accidentally had a minus sign where there should have been a plus. So those are our models of the different horizons of our universe. If your computer is better than the toaster that we used, we will leave the Python script as a notebook in the description, and you can try it out yourself. We fixed all of the mistakes that we mentioned, and some that we didn't mention, so hopefully the program should give you the right results. Now, don't take these graphs as a perfect description of the horizons. In our case, it might be better to imagine them yourself. Because as long as you remember all the restrictions imposed on the horizons, you will get to a pretty good simulation of these horizons. From what we know, the universe will accelerate its expansion all the way to the end of time, making the force at which things get pulled apart ever increasing. The Milky Way will eventually be pulled so heavily away from the rest of the universe that we cannot even see our neighboring galaxies. For a long time, gravitation will keep the Milky Way together, but even that won't be strong enough forever. Eventually the Earth will be pulled away from the Sun. Later, we will be thrown off the face of the Earth. And if we wait long enough, even molecules won't hold. Now here comes the great part. At some point, long after we're all dead and gone, there will be a force powerful enough to pull the glucose and starch apart from each other, but not strong enough to break down the individual glucose molecules. Bread will be pulled apart and turned into sugar. At one glorious point in time, all bread will become sugar. These are the facts and the consequences of the cosmological horizons. They are fascinating and scary, but that's cosmology for you.